Hello, my name is Arturo Garcia, and I will be presenting you guys my real-world static analysis presentation. So my object of choice for this project was a concrete patio table located down the street in my neighborhood. I figured that it would be an interesting structure since it is really heavy and sturdy, and it seems like it would take a lot of force to even move it. The knowns can be that the patio table is not fixed to the ground, nor is the tabletop fixed to the table stand in the middle. We know two forces pointing downwards, which would be the weights of both the tabletop and the stand. The weight of the tabletop is 175 pounds, and the weight of the base will be 142 pounds. For the unknowns, I could assume that the force produced from the wind can be an unknown acting on the table, the direction in which the wind is traveling, and what force would keep the table from moving. So in this initial free body diagram, I drew the forces uh, acting from the table, which would be the weight of the tabletop going down and the weight of the base going down. I estimated that the forces of the wind would be applied towards the center of each object of the table. For the assumptions, the whole patio table is made of pure concrete and is not hollow in the inside. Patio table is not rigidly placed on the ground, so therefore this means that the system will not have any moments. The weight of the tabletop is 175 pounds and the base is 142 pounds, so the total weight will be 317 pounds. The dimensions for the tabletop will be 42-inch diameter and a thickness of 3 inches. The stand is 26 inches high and has a diameter of 16 inches. Wind loads are to be distributed uniformly across all the components of the structure. The strongest wind speed recorded in El Paso that I figured out was 84 miles per hour on March 26, 2010. The wind direction was headed towards the west on that specific day, actually, and there has to be a static friction force acting on the table as the wind is applied. So, in order to solve for this static analysis, I needed to find a wind load calculator, and once I did, the specific one I found, I had to convert my miles per hour to meters per second and find the surface area of my structure. To convert miles per hour to meters per second, I did this simple conversion, which put in my 84 miles per hour over here and converting it to kilometers, then multiplying it by 1,000 meters and doing your time conversions, and I got 37.6 meters per second for my wind speed. And I assumed that each component of the table, being the tabletop and the base, were perfect cylinders, and I used the equation for the surface area of a cylinder, and I got this value for the tabletop and this value for the table stand. Now for the updated free body diagram, I still have the forces or the weights of the tabletop and the base going downwards. Plugging in the values in the wind load calculator, I got this amount of force hitting the center of the base and this amount of force hitting the center of the tabletop. And now I would just need to find the amount of static friction going the opposite direction. So in order to solve, I did the sum of the forces in the z, which is basically the weight of the whole table going downwards. That's why we have a negative value of negative 317. There is no sum of the forces on the x. And for the sum of the forces on the y, I got the two wind loads applied to the structure minus the static friction. So in order to find the force of static friction in equation 5, to prove that the table will remain static, I will need the formula for static friction and the coefficient of concrete, which is the formula right here for static friction. So for the coefficient of concrete on concrete in a dry condition will be 0.80. So you will plug that value into your equation times the weight of the table and you get this negative value of negative 253.6. Plugging that value into our sum of the forces on the y, once I added up everything, I got a positive value of 345 pounds. So based on this answer, it came out positive. So this means that the force of wind was greater than the force of friction acting on the patio table. So based on this answer, it means that the patio table will most definitely be a static failure since the amount of static friction was not strong enough to overcome the amount of the force that the wind applies on the table. So that will conclude that this structure will most likely be a static failure and tip over. Thank you for taking your time to watch my video.